Mathematician David Hilbert said, "The infinite, no other question ever moved so profoundly the spirit of man." In this lesson, we're going to compute interest on an account that is continuously compounding, all to answer the question, how can interest be compounded continuously? Before we jump into it, let's make sure we're ready for this lesson by looking at warm-up number 2, the cube root of a when a is 8. This means we're trying to find the cube root of 8, which is 2. And we're going to find a to the bc power when a is 9, b is negative 2, and c is 1/4. This means 9 to the negative 2 times 1/4, which is 9 to the negative 1/2 power. This would look like 1 over the square root of 9, which is 1 over 3. Now let's take a look at a problem that you will be able to do by the end of this lesson. So, if you deposit $1,000 at 2.3% interest, compound continuously, what would your ending balance be to the nearest cent after 5 years? This means we're trying to find the limit as x approaches infinity of 1,000 times the sum of 1 and 0.023 over an infinite number of compoundings to an infinite exponent. So we're going to use the formula b is equal to p times e to the n, where n is equal to rt, meaning we actually have b is equal to p times e to the rt power. This gives us 1,000 times e to the 0.023 times 5 power. Using the TI-30XS, we get to do 1,000 times, we have an e to the exponent button as a second. So second to get to that e to the x. Then in the exponent, we open parentheses, put 0.023 times 5, close parentheses, and hit equals. We get $1,121.87. Compounding interest daily makes money grow more quickly than simple interest. It is possible to compound interest every hour, every minute, every second. There are over 31 million seconds in a year. The compound interest formula works with seconds just as it did with days. There are 1 million microseconds in 1 second. It works even if interest is compound every microsecond. How do millions of compounds affect the ending balance after a year? To understand this, we need to learn about limits. Imagine you want to walk all the way across a 64-foot wide room. The length, 64 feet, is a finite distance. It can be represented by a real number. To do this, you must first walk halfway across the room, or 32 feet. To continue the walk, you must cover half the room, remaining 32 feet, which is 16 feet. Then you must cover half the remaining 16 feet, which is 8 feet. Next, you must cover half the remaining 8 feet, which is 4 feet. Then you need to cover half the remaining 4 feet, which is 2 feet. Next, you need to cover half the remaining 2 feet, which is 1 foot. Then you need to cover half a foot, then a quarter foot, then an eighth of a foot, and so on. The distance walked so far are shown in this diagram on the screen. What do the 3 dots at the end of the expression mean? Because there will always be some distance between you and the wall, no matter how small, you will always have a positive number to take half of. You will take half of the remaining distance infinite many times. Yet you know you can touch the wall you were walking towards. And you know it is 64 feet away. Conclusion, you can add up all the infinite amounts of numbers and get a finite sum. The infinite sum shown adds to 64. If you stopped adding at any time, you would not reach the sum of 64. The limit of the sum is 64 since every addition gets the sum closer to 64. The finite sum will never reach 64. Now think about compound interest. Rather than compounding every minute or every microsecond, imagine compounding infinitely many times in a year. This is called continuously compounding. Will it make you rich? Consider if you deposit $1,000 at 100% interest, compounding continuously, what would your ending balance be after 1 year? Notice the extremely high interest rate. Compare your guess with the guesses of those around you. The question just posed is answered through a series of examples we're about to do. Be sure to compare your guesses with the correct answer. Given a quadratic where f of x is equal to x squared plus 3x plus 5, as a value of x increases to infinity, what happens to f of x? Well, let's start out with if x is 100. We would wind up with 10,305. This is because 100 squared plus 3 times 100 plus 5. If we tried when x was 1,000, then we would get 1,003,005. What about 90,000? Then we get 8,100,270,005. So f of x has no limit. Let's check your understanding. And as the value of x increases towards infinity, what happens to the value of g of x if it is negative 5x plus 1? Well, when x is 1, we're going to get a negative 4 for g of x. This is because negative 5 times 1 plus 1. When x is 10, we're going to get a negative 49. And if x is 100, we get a negative 499. So we can confidently say that g of x decreases. A function is a rule that assigns a unique number of a range to each element of the domain. In the first example, we looked at the limit of a polynomial function. A rational function is an algebraic function which is both a numerator and a denominator are polynomials. Here are some examples. In general, a rational function has the form f of x is equal to g of x divided by h of x, where g of x and h of x are polynomials, and h of x cannot equal 0. Notice that the values of x where the polynomial in the denominator equals 0 are excluded since division by 0 is undefined. In the next example, we're going to examine limits of a rational function. Given the function f of x is equal to 6x minus 1 as the values of x increase to infinity, what happens to the value of f of x? Well, if x was 100, then we would get 1.98, and this is because we would have 6 times 100 minus 1 in the numerator and 3 times 100 plus 2 in the denominator. When x is 1,000, we would get 1.998. Well, when x is 90,000, to make a big jump, we get 1.99998. What about if x was 2 billion? Then we would get 1.9999999. So we can see that f of x approaches 2. It gets very close. This means the limit as x approaches infinity of f of x, then we get 2. Let's check our understanding of this and see what happens if f of x was equal to 1 over x and create a new table using our calculations to find the limit as x approaches infinity of f of x. So when x is 1, f of x is equal to 1 because we would have 1 divided by x, which is 1. If x was 2, we'd have 1/2. 10, we would have 1/10. 100, we would have 1/100th. 10 million, and we would have 1 over 10 million. So we can see the limit as x approaches infinity of f of x is getting smaller and smaller and smaller till it's almost but never quite 0, meaning the limit is 0. Given the function f of x is equal to 2 to the x power, can we find the limit as x approaches infinity of f of x? Well, if x is 1, then f of x is 2 because we would have 2 to the 1 power. And if x was 100, then we would wind up with 2 to the 100th, which is a super high number that the calculator's not going to give you an answer to. So it goes to infinity, meaning it's also undefined. Let's check our understanding and say given f of x is equal to 1 to the x power, can we find the limit as x approaches infinity of f of x? So when x is 1, then f of x is 1 because we have 1 to the 1 power. And when x is 10, we get 1 because 1 to the 10th power will give us 1. If x is 100, we get 1 because, again, 1 to the 100th power. This means that the limit as x approaches infinity of f of x is 1. That was rather simple and straightforward. What if f of x was equal to the sum of 1 and 1 over x to the x power? Can we find the limit as x approaches infinity of f of x? Well, if x was 100, then we would get 2.7048. And this is because we would have 1 plus 1 over 100 to the 100 power. When x is 1,000, we would get 2.7169. And when x is 90,000, we would get 2.7182. We can look at two separate parts. One, the limit as x approaches infinity of 1 over x is 1, and the limit as x approaches infinity of 1 over x is 0. So the limit as x approaches infinity of 1 plus 1 over x would be equal to 1. Now, e is a special number in math that is approximately 2.71828. So the limit as x approaches infinity of the sum of 1 and 1 over x to the x power would be equal to e. Let's check our understanding of this, and we're going to find the limit as x approaches infinity of 1 plus 0.05 over x to the x power and round to 5 decimal places. Let's try what happens when 90,000 is equal to x. That means we're calculating the limit as x approaches infinity of 1 plus 0.05 divided by 90,000 to the 90,000 power. This is going to give us 1.05127. Now let's compute interest on an account that is compound continuously. If you deposit $1,000 at 100% interest compound continuously, what would your end balance be after 1 year? That means we're trying to find the limit as x approaches infinity of 1,000 times the sum of 1 plus 1 over x to the x power. Let's remember that 1 plus 1 over x to the x power is e. This means we can have 1,000 times e. Remembering the value of e, we get approximately $2,718.28. Let's check our understanding of this. The irrational exponential base e is so important in mathematics that it has a single letter abbreviation, e, and it has its own key on the calculator. When you studied circles, you studied another important irrational number that has a single letter designation and its own key on the calculator. That number was pi. Recall that pi is approximately 3.141592654, and it goes on infinity. Use the e and the pi keys on your calculator to find the difference between e to the pi and pi to the e, and round to the thousands. On the TI-30XS, we see that there's a problem because we have an e to the x power as a second function. With nothing to put there, we can simply put a 1 in and hit enter. This is going to give us approximately 0.6815. So if you deposit $1,000 at 2.3% interest, compound continuously, what would your ending balance be to the nearest cent after 5 years? This means we're trying to find the limit as x approaches infinity of 1,000 times the sum of 1 and 0.023 over an infinite number of compoundings to an infinite exponent. So we're going to use the formula b is equal to p times e to the n, where n is equal to RT, meaning we actually have b is equal to p times e to the RT power. This gives us 1,000 times e to the 0.023 times 5 power. Using the TI-30XS, we get to do 1,000 times. We have an e to the exponent button as a second. So second to get to that e to the x. Then in the exponent, we open parentheses, put 0.023 times 5, close parentheses, and hit equals. We get $1,121.87. Let's check our understanding of this. Craig deposits $5,000 at 1.12% interest, compound continuously for 4 years. What would his ending balance be to the nearest cent? Now we already know that the formula is b equals p times e to the RT power. And in this case, the principal amount is 5,000, the rate is 0.0112, and the time frame is 4. We substitute those values into the equation, and doing a little bit of calculator kung fu, we get $5,229.09.